Welcome to online lecture series in organic chemistry, and we are discussing about the electronic spectra of complexes. In earlier video we have seen the selection rules for electronic transitions, that is the Laporte orbital selection rule and the spin selection rule. In this video I am going to start the new concept, that is electronic states and terms for the polyelectronic atoms or multi-electronic atoms. Actually, you know that other than hydrogen, all the atoms contain more than one electrons. Only in hydrogen atom or that element there is a one electron, whereas other elements, helium or lithium, like that, carbon, nitrogen, these contain multi electrons, more than one electrons. And what are the electronic states or energy levels and terms for polyelectronic atoms? That part we are going to start. Now, before discussion of these electronic states, meaning of electronic states and how these are different than the energy levels considered for writing electronic configuration, first of all you must know about the quantum numbers, basics about the quantum numbers. You know there are four quantum numbers: principal quantum number, azimuthal quantum number, magnetic quantum number, and spin quantum number. First of all, what is principal quantum number denoted by small n? This principal quantum number, it describes the main energy level or shell that the electron is found in. You know, at the center of atom there is a nucleus. Electrons are revolving around the nucleus according to Bohr's atomic model, and electrons present actually in the main energy level or shells, and these shells or main energy levels, these are designated by principal quantum number. You know, here suppose this is the nucleus and these are the energy levels, main energy levels. These are described by principal quantum number, that is n equal to 1, 2, 3, 4, 5, 6, 7, and corresponding designations are K, L, M, N, O, P, and so on. So these are the main energy levels. Now in a given shell or main energy level, there are 2n square number of electrons. For example, in first shell there are 2 electrons, in second shell there are 8 electrons, in third shell there are 18 electrons, and in fourth shell there are 32 electrons. This part you know. Now second important quantum number, it is the azimuthal quantum number or orbital quantum number or subsidiary quantum number. Now this quantum number describes the orbital angular momentum or shape of the subshell. Actually, in shell there are subshells like S, P, D, F. These are the subshells. S subshell, it is spherically symmetrical. P, it is dumbbell shape. D, it is double dumbbell shape, and 3 subshell has 3-dimensional complicated structure. So this quantum number, azimuthal quantum number, gives informations about the subshells present in the shells. So it represents the subshell to which electron belongs and defines the shape of the subshell. Now again, important thing is there are n number of subshells in a given shell. For example, suppose there is a second shell. For second shell, value of principal quantum number, it is 2. N is equal to 2. It means in second shell there are 2 subshells, or value of L, that is azimuthal quantum number, ranges from 0 to n minus 1, where n is principal quantum number, and in a given shell there are n number of L values. Meaning of this is, in given shell there are n number of subshells. Now when value of L, it is 0, 2, 0, 1, 2, 3, then corresponding subshells are S, P, D, F. If L is equal to 0, then corresponding subshell is S. Similarly, when L is equal to 1, subshell becomes P. When L is equal to 2, then name of subshell is D. When L is equal to 3, the name of subshell is F. And number of shells, say for example 1, 2, 3, 4, these are the shells, and in first shell there is only one subshell with L is equal to 0, that is S. In second shell there are two subshells, that is SP. In third shell there are three subshells, SPD, and in fourth shell there are four subshells, SPDF. It's like that. So this is the azimuthal quantum number. And the third important quantum number is magnetic quantum number, denoted by small m. This magnetic quantum number, it represents the orientation of an orbital in space. Actually, in subshell there are orbitals. For example, in S subshell there is S orbital. In P subshell there are P orbitals. 3 P orbitals are there, Px, Py, Pz. In D subshell there are D orbitals like dxy, dyz, dzx, dx square minus y square and dz square. 5 D orbitals are there. Similarly, in F subshell there are 7 F orbitals. So this magnetic quantum number gives information about or represent the orientation of an orbital in space. Now this value of m ranges from minus L to plus L through 0. What it means? If L is equal to 1, that is for P subshell, then there are three possible m values, that is minus 1, 0 and plus 1. These are the three possible m values, and when the value of m is minus 1, the corresponding orbital will be Px. When it is 0, then Py, and when it is plus 1, then Pz. So Px, Py, Pz, these orbitals are described by value of m, that is minus 1, 0 and plus 1 respectively. Now for given value of L, there are 2L plus 1 m values. It means when L is equal to 1, the number of m values are 3. As per this formula, when we substitute value of L as 1, so 2 into 1, that is 2 plus 1, that is 3. So 3 m values. It means when L is equal to 1, that is for P subshell, there are 3 m values. It means in P subshell there are 3 p orbitals. It is like that. Now consider this table. So value of L 0, 1, 2, 3, these are the subshells, that is S, P, D, F, and for when L is equal to 0, that is for S subshell, the number of m values are 1, that is 0. So m is equal to 0 means it is S orbital, and when L is equal to 1, 3 m values are there. It means there are 3 p orbitals. Accordingly, the values of m are minus 1, 0, plus 1, and the orbitals are Px, Py, Pz. If L is equal to 2, that is D subshell, in D subshell there are 5 D orbitals with m values minus 2, minus 1, 0, plus 1, plus 2, and corresponding D orbitals are dxy, dyz, dzx, dx square minus y square and dz square. Similarly, if L is equal to 3, that is F subshell, in F subshell there are 7 F orbitals with m values minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3, and corresponding F orbitals are fx cube, fy cube, fz cube, fx into bracket y square minus z square, fy into bracket z square minus x square, fz into bracket x square minus y square, and fxy z. So these are the 7 F orbitals. So remember, in shell there are subshells, in subshell there are orbitals, and the description of orbital, it is given by magnetic quantum number. And the fourth quantum number, it is the spin quantum number, that is small s. Now, in an atom, electrons present in shells there are subshells, in subshell there are orbitals, and in each orbital maximum 2 electrons can be accommodated. Out of 2 electrons, 1 electron can spin along the clockwise, other spin along the anti-clockwise direction. So the spin quantum number tells about the spin of electron around its own axis. Now when electrons spin around its own axis along the clockwise direction, then the s value, it will be plus half, and when it spins in anti-clockwise direction, then s is equal to minus half. So here you can see when electron spin in clockwise direction, it is also represented by arrow pointing up, and for this electron S is equal to plus half. When electrons spin along the anti-clockwise direction, it is also represented by arrow pointing down, and for this electron the S is equal to minus half. This is the spin quantum number. So this is about the brief introduction to the quantum numbers. Now what is the role of quantum numbers? Actually, quantum number, it is the perfect address of electron in an atom, and you know this position of electron, it is described by electronic configuration. So electronic configuration, it is the assignment of the given number of electrons to a certain set of orbitals, and this electronic configuration, it is based on three important rules or principles, that is above principle, Pauli's exclusion principle, and Hund's rule of maximum multiplicity. And you know that according to above principle, the electrons occupy the orbitals of lowest energy level first. It is the above principle. According to Pauli's exclusion principle, Pauli's exclusion principle, it states that no two electrons in an element can have all the four quantum numbers same. It means in an atom, suppose there are several electrons, but out of various electrons there will not be two electrons have same set of all the four quantum numbers. At least one quantum number must be different for the second electron. This is the Pauli's exclusion principle. And Hund's rule of maximum multiplicity, it is applicable for the filling of electrons in degenerate orbitals like p, d, f, etc. And according to Hund's law of maximum multiplicity, there is no pairing of electron unless all the available orbitals of equal energy are singly occupied. Or according to Hund's law of maximum multiplicity, which states that the electrons occupy the orbitals with parallel spin first before being paired. This is the Hund's rule. So this electronic configuration, it is based on these three principles or rules. Now most important thing is, what are the electronic states now? Now electronic states, these are somehow different from the energy levels considered for writing electronic configuration. Now in electronic configuration, electronic interactions are not considered. You know, if suppose in s orbital there are two electrons, when this s orbital is completely filled, then in between two electrons there is a possibility of inter-electronic interaction, especially there will be repulsion between two electrons, and this repulsive force, it is not considered while writing electronic configuration or while considering energy levels to assign the electronic configuration. Not only there is interaction between two electrons, there is interaction between the electronic spin with the orbital angular momentum. This interaction is also not considered in the electronic configuration. So energy states, these are the energy levels resulting from the electron-electron interactions and magnetic interactions. These are the energy or electronic states, and these electronic states are somehow different than the energy levels considered for assigning electronic configuration, and this and therefore the quantum numbers that we discussed right now, these are to be modified, need to be modified, and the new quantum numbers are resultant spin quantum number, resultant orbital angular quantum number, then spin multiplicity, and total angular momentum quantum numbers. So these quantum numbers are required for the considering the electronic states, new electronic states where there is a consideration of electronic interactions. Next video we are going to discuss in detail about the electronic states and term symbols.